Welcome to AI Paper Podcasts. We cut through the jargon of academic papers and get you straight to the core ideas in AI research. Today, we're jumping into a really interesting one, Made-Peel, learning dexterous manipulation from egocentric videos. And just for a quick summary up front, maybe for those short on time, this paper, Made-Peel, it's all about tackling, how to teach robots really fine-grained dexterous skills. Think complex hand movements, the main idea. It's pretty cool, actually, learning directly from huge data sets of human first-person videos. So seeing how we handle objects. What's really key here is that Made-Peel isn't just showing off in simulation. They've built new, tough benchmarks, and they show it working in the real world with a complex robot hand. That's a big step.
Yeah, that real-world part is often missing.
Exactly. Plus, they've released their code, the model, the benchmark, everything, which is, fantastic for the research community. So essentially, Made-Peel gives robots a way to learn these tricky hand-object interactions just by watching us, potentially making them way more capable.
Okay, so let's unpack this a bit more. Why is teaching robots this kind of dexterous manipulation so incredibly hard? We're not just talking about picking up a big, simple box, right? This is way more subtle.
Absolutely. Think about stirring spaghetti in a pan carefully or ironing clothes. It requires really fine control, tiny adjustments in grip, pressure.
Yeah, things we do without thinking.
Exactly. Imagine trying to get a robot to, say, assemble tiny electronics or even assist in surgery. That's the level of dexterity we're aiming for, and it's a huge challenge.
And you mentioned a key problem is generalization.
Right. That's probably the biggest hurdle. Most current systems, especially for these fine motor skills, they really struggle to apply learning from one task to another, or even to slightly different objects.
So they need tons of specific training data for every single thing. Pretty much. Often very specific hand-engineered data. And that just doesn't scale, does it? I mean, think of all the different things we do with our hands every day.
No way.
So that's why people got interested in egocentric videos, the first-person view. It inherently captures that intricate dance between our hands and objects. It's a potential goldmine of data.
Okay, so if these egocentric videos are so rich in information, why haven't they completely solved the dexterity problem before Made-Peel? What was missing?
That's a really good question. So while the data sets are rich, a lot of the previous approaches using them didn't have a specific, let's say, explicit focus on the dexterity part, the really fine-grained control.
How so? What were they doing instead?
Many methods were more implicit. They might learn general visual features or representations from the videos, which is useful, but you can't directly use those features to tell a robot exactly how to position its fingers.
Okay. So it's like getting the context, but not the precise instructions.
Precisely. You typically need another layer, like reinforcement learning or imitation learning, trained on top of those features to actually get a control policy for the robot. It's sort of a step removed.
Got it. That makes sense.
And there was another issue, too.
Which was?
The way we measure success. The benchmarks. There's been a real shortage of good, comprehensive benchmarks, specifically for dexterous manipulation.
You mean the tests they use?
Yeah, a lot of existing ones use really simple grippers, like two-finger pincers, low degrees of freedom, or low duff.
Okay.
And while that's fine for some tasks, it just doesn't cut it when you're trying to control a complex, multi-fingered hand that's more like a human's. You can't really test true dexterity that way.
Right, you need tasks that require that complexity.
Exactly. And that gap was a big motivator for the Made-Peel authors. They saw the need for better benchmarks and ways to train for these complex hands, especially in the real world.
Okay, so we have these hurdles. Generalization, the indirectness of prior learning from video, the lack of good tests. How does Made-Peel actually, bridge these gaps? How does it use those human videos to teach these skills?
So Made-Peel's core idea is to extract what they call dexterous manipulation priors directly from watching humans. It's like digging deeper into the videos to pull out the fundamental principles of interaction.
Priors, like underlying rules or common patterns.
Kind of, yeah. Robust patterns about how and where a human hand interacts with an object to successfully manipulate it. It's trying to learn the physics of interaction from observation.
And they use these concepts of a contact frame and a prediction frame to do this, right? Can you break that down? That sounds important.
Yes, very important. So FC, the contact frame, that's simply the moment the hand first touches the object in the video. Pretty straightforward.
Okay.
But FP, the prediction frame, is the clever part. It's an earlier frame in the video when the hand is still some distance away.
Why look back? Why not just focus on the contact?
Because it forces the system to anticipate. to predict what the hand should look like and where it should aim before it makes contact. Just like we do, right? We shape our hand before we grab something.
So it's learning the approach, not just the grab.
Exactly. It's about planning the grip and movement ahead of time, not just reacting at the last second.
So how does it technically work? They find the hand pose and contact points at impact, and then trace back.
Precisely. They extract the hand pose, they call it HSC, and the specific contact points, PDC, right at that contact frame FC. Then, using point tracking techniques, they project those contact points backwards in time to the earlier prediction frame, FP.
To get PTP.
Right, PDP, which represent the future contact points viewed from that earlier moment. This gives the system training data. Given this scene, predict this future hand pose, HSC, and these future contact points, PDP.
That's clever. And they use existing tools for finding the hand and the contact.
Yeah, they leverage off-the-shelf models for things like segmenting the hand and object contact, and for estimating the hand pose itself. They specifically use Mano poses.
Mano.
It's a standard parametric model. It can generate realistic 3D human hand shapes and poses, which helps standardize things.
Okay, but human hands, they vary so much, right? Size, shape, the way we grip things. How does Maypeel accurately predict the pose itself? That sounds really difficult, like trying to predict an exact 3D shape.
That's another area where they made a smart simplification. Instead of trying to directly regress or predict the exact continuous parameters of the hand pose.
Which sounds hard.
Very hard, yeah. They turn it into a classification problem using something called a hand pose tokenizer.
A tokenizer. Like breaking words into tokens.
Kind of analogous, yeah. Imagine they have a big library or code book of common anatomically correct hand shapes observed in the training data. Instead of predicting infinite variations, the model just needs to pick the best pose from this predefined list.
So it simplifies the output space. Choose from column A, B, or C rather than drawing anything.
Exactly. It makes the learning problem much more manageable. It's selecting the most appropriate hand gesture token for the situation. They mentioned it's similar to tokenizers used for human body poses.
Makes sense.
Yeah.
And how is the model actually trained? What tells it if it's making good predictions? You mentioned loss functions.
Right. There are a few key ones. There's LCON PTP. That's a cross-entropy loss specifically for predicting those contact points, focusing on the thumb and index finger, which are obviously crucial for dexterity.
Okay.
Then there's LHand, also cross-entropy, but this one is for predicting the correct hand pose token from that library we just talked about.
Got it. Pose and points.
And then there's a really interesting one, LCTR, a temporal contrastive loss.
Temporal contrastive. What does that do?
So their visual encoder uses pre-trained weights from models like Dino, which are known for creating features that are good at distinguishing different images. This LCTR loss helps maintain that distinctiveness over time.
So it learns the dynamics, not just static poses.
Exactly. It helps the model understand that interacting with an object is a sequence, a process. It encourages the features learned for different moments in the interaction to be distinct. It helps prevent the model from just blurring everything together.
That sounds important for smooth control.
Definitely. And the total loss is just a combination of these weighted appropriately. They use a standard vision transformer, a VITB16 as the encoder, starting with those Dino weights, and a transformer decoder to make the predictions.
Okay, this all sounds very well thought out. But now for the big question. Does it actually work? How did they test Maypeel? You said they went beyond simulation.
Absolutely, and this is where it gets really compelling. First, the training data. They used the Ego4D data set. Massive data set, over 3,000 hours of first-person video of people doing everyday things.
Wow.
They used about 1,600 hours of that, which gave them around 82,000 training samples. So it's learning from a huge amount of diverse, real-world human behavior. That's crucial for generalization.
Definitely. And the simulations. They didn't just use the old benchmarks.
They did test on existing ones like DAPG and MetaWorld, just to show it works broadly, but crucially, yes, they designed new simulation tasks specifically to test high-level dexterity, filling that gap we talked about.
Like the ones in the paper. The pan, the brush.
Exactly. The pan task, lift a pan, place it on a stove. The brush task, pick up a brush, make a brushing motion, and iron, using a clothes iron on some pants.
Those sound genuinely tricky.
They are. They require much more fine-grained control and coordination than just picking something up with a simple pincer. The success criteria are also pretty demanding, getting the pan bottom near the stove, the brush tip contacting the board correctly, the irons sliding along specific markers.
And the the real world, the ultimate test. How did that go? Because simulation success doesn't always translate, right?
Right, the dreaded sim-to-real gap. But this is a real strength of the paper. They did extensive real-world validation.
What was the setup like?
They used a mimic robotic hand. It's a commercially available dexterous hand mounted on a Franca Imica Panda arm, standard research robot arm. They had a couple of external cameras watching the scene.
And the hand itself? Lots of joints.
Yeah, the arm has 7 degrees of freedom, and the mimic hand has 16. 16 joints just in the hand to control. They controlled it at 10 hertz.
16? Wow. Okay, what tasks did they try in the real world?
They chose tasks that really push dexterity and haven't been explored much with these complex hands. One was plush, picking up a soft plush toy, good for testing robustness to new shapes and deformable objects.
Okay.
Then pan again, but for real. Grab the handle, lift it, place it on an induction stove.
The same as the sim task.
Pretty much, yeah. Good test of transfer. And finally, brush, again mirroring the simulation. Pick up the brush, move it, and perform the brushing motion. They know this was the most challenging, really testing the grasping precision and the fine control needed.
Yeah, I can imagine. The photos in the paper showing the hand doing this are quite impressive.
So overall, the results were strong. It showed benefits across the existing sim benchmarks, proving its general applicability.
And what about understanding why it worked? Did they look at the impact of the different parts, like that tokenizer or the lost terms?
Yes, they did an ablation study, which is always illuminating. It's in table 2 in the paper. For example, the L-hand loss, the one for predicting the hand pose token. They found it was really helpful in the dexterous tasks.
Makes sense.
But interestingly, it could sometimes slightly hurt performance on simpler, non-dexterous tasks.
Huh. So optimizing for high dexterity isn't always the best for everything.
It seems that way. It suggests the tokenizer really specializes the model for complex manipulation.
Fascinating. What about predicting the contact points?
Elkin. Yeah.
Remember that one, Elcon AQP? They found that just randomly guessing contact points was, unsurprisingly, much worse than their method of using the projected fingertips. And critically, predicting contact for both a thumb and index finger was better than just predicting a single point.
So the detail matters. More fingers, better prediction. Exactly. It highlights that planning for multi-finger contact is key for achieving that human-like dexterity. They also did some error analysis on how they get the training data from the videos.
Finding where things go wrong in the supervision.
Right. Things like the system thinking the hand touched itself, or clothing instead of the object, self-contact, or detecting contact too early, or losing track of the hand while it's still touching. They acknowledge these errors can bias the learned features and suggest improving the supervision extraction is an important next step.
Okay, so we've really dug into Mapley here, seeing how it learns complex, dexterous skills by essentially carefully watching humans. It feels like a very direct route to getting robots to be more capable with their hands. Definitely helps us get well informed on this specific research front.
Indeed. And stepping back, looking at the bigger picture, this kind of work really lays important groundwork. It strongly suggests that for these really complex real-world robot tasks, especially the ones needing that human touch, that human dexterity, distilling these detailed interaction patterns, these priors, directly from observing humans, particularly using egocentric video, seems like a really powerful way forward. We're teaching robots by showing them the best examples with us, doing things naturally.
And for you listening, maybe think about this. As robots get better at these human-like skills, learning from how we do things, what does that unlock? Could we see robots helping out in the kitchen, preparing complex meals, assisting surgeons with even greater delicacy, or maybe building intricate things on construction sites or in factories with a precision we haven't seen before from machines? What possibilities really stand out to you when you think about robots gaining this kind of learned dexterity? Something to mull over.